So with the idea of disjoint and not disjoint events in mind, we can talk about how to compute probabilities where we want one thing or another. And we can chain this further like we did with the multiplication rule, though generally we're going to stick to two cases at once. Where if we have disjoint events, A and B, the probability of getting A or getting B is just the sum of those probabilities. It's PA plus PB, because we can get one or we can get the other, and that's really all we have to worry about. There's no other combination of things that can happen. And a really basic but vitally important example of this is thinking back to our work with complements, where we defined a complement as being the probability of some event not happening. And in particular, we say that 1, the total probability, is equal to the probability of the event plus the probability of its complement, because you get one or the other, and those are definitely disjoint, because I'd like to think it's, or at least it would be, incredibly strange to imagine having an event and a not event, that is, an event happen and also not happen simultaneously. I don't want to think about that too much. It makes my head hurt. I can't quite get out a sentence that even says that paradox effectively. For a less let's say, mind-bending example, you just think of a coin flip, where when you flip a coin, generally speaking, still leaving room open for magic even though it hasn't happened yet, your options are heads or tails. And yes, technically it's possible for the coin to land on its side, and there are misprinted coins that have their own weird nonsense to them, but assuming we're talking about a fair, regular coin, you can either get heads or you can get tails. So if you want to get the probability of heads or tails on a coin flip, that would be the probability of heads plus the probability of tails, where this is actually an example of that complementary idea, because generally speaking, these are complements of each other. You can think of tails as not heads, in the same way you can think of heads as not tails, because there's only two of them. But in any case, it's just 1/2 plus 1/2, or if you prefer, and most people do, 1. Because, well, short of the side landing, something's got to happen. On the other hand, if we have non-disjoint events A and B, then when we want to look at the probability of A or B, we take the probability of A plus the probability of B minus the probability of both. And some people are going to see that and immediately understand why that happens, but for a lot of people, that's probably not obvious. Where the reason why this happens is if these events are not disjoint, then there are situations in which you can have one and the other. So when you're counting the probability of the one, PA, you're getting a little bit of PB. And then when you count PB, you get a little bit of PA.
You got peanut butter on my chocolate.
Well, you got chocolate in my peanut butter.
So in each of these, you're getting a little bit of the other. You got to make sure you don't count that twice. And to get a better picture of what that looks like, in my opinion, the easiest thing to do is to think in terms of a Venn diagram, where we'll say that the red here are all of the ways that A can happen, and the green will be all of the ways that B can happen. Where if these are disjoint events, that overlap in the middle doesn't happen. There's no overlap because they can't happen simultaneously. But because these are not disjoint, you can see that if we want to talk about all of the ways that B happens, as well as all of the ways that A happens, well, that's a bit unfortunate, because A has a little bit of B, and B has a little bit of A. Getting a bit of the chocolate in the peanut butter and peanut butter in the chocolate. We got to figure out how to handle this Reese's Cup situation. Because when we want to count either, we don't want to overcount both. So that's why we remove that extra case. And to get a bit more concrete about it, we can think of another really basic example here, where let's say that instead of tossing a coin, where obviously there are very few options, I want to throw a die again. And let's say that the events I want to look at here are throwing the die and landing a 3, or landing an odd number. Well, if I want the probability of 3 or odd, I have to understand that, well, thankfully 3 is pretty simple. It's just one way that you can get a 3. But then when we talk about odd numbers, looking at the odd numbers from 1 to 6, and we've got 1 for sure, we've also got 5 for sure, but we're also stuck with 3. So when we're counting the odds, we're getting 3 again, which means that when we're counting either, we're counting 3 too much. So we need to remove one overlap case. It just happens that one overlap case for 3 and odd means we're removing 3 from here, essentially. Hey, I got a 1 that time. Fits my example better than the other one did. But point is, probability of 3, 1 in 6, plus probability of odd, 3 out of 6, but we don't want to get that 3 in there twice, so we remove one of those out of 6, and you just get 3 out of 6, or 1/2, which makes sense. Because if you want 3 or odd, the 3 is completely redundant in the odd selections. So really, you're just looking at the probability of 3. Thinking of it in terms of these Venn diagrams, that would be like if A was entirely inside of B, instead of just having some overlap. But next, we're going to look at a couple of examples that have a tiny bit more to them.